In this video, we're going to have a look at my Heathkit IO-102 scope. And I'll talk to you a little bit about some of the things I've done over the years to keep it running and in good in perfect working order. A little bit of background: this is my original IO-102. I remember actually this kit was given to me as a birthday present by my parents, and I then built it in 1974. And I remember the only other piece of test equipment that I had at the time was a Heathkit IM17 transistorized voltometer, which was a high impedance FET input, 11 megohm, very nice little thing, which is you probably can see on other YouTubes. It'll pop up from time to time on mine. It still works, by the way. And so all I had to actually align this and build it was a voltmeter. And that's actually all Heathkit actually requires you to have, although if you have a signal generator, I'm sure that would be nice too. Anyway, so yes, this scope is 50 years old, and it works perfectly. We're going to look at some of the things I did. The immediate things you can see right away, and I kind of do this with all of my old Heathkits when comes time to clean them up and get them spruced up a bit, is I put all new shiny 632 and 832 Phillips head hardware all over the place, because it's nicer. After 50 years, the original Heathkit zinc plated screws kind of look sort of really crappy. So this kind of breathes a little bit of new life into this. So this worked fine, and then of course over the years, over the decades, I've moved and had a family, and you know, at some point the scope went into the basement with a lot of other stuff, and it stayed there. And 10 years ago I decided, okay, let's pull this out of the basement and see what happens. And not really caring much, I plugged it in and powered it on. And the little pilot light on the top right there, it came on, but there was nothing. The thing other than that was as dead as a doornail. So I'll talk to you about how I troubleshot it and got it working again. I'll show you exactly what failed. And while I was in there, as well as putting in new shiny screws 10 years ago, I decided to also take a look at the AC input section. I sort of revamped that a bit, and you'll see that, and we'll give you a little bit of a tour of the innards of the IO-102. In case you're curious as to what's being displayed right now, well, it kind of looks sort of like a sine wave. In fact, you can see from the banana plug jumper, it's basically displaying its built-in so-called 1 volt peak-to-peak output. So right here, the scope gives you a 1 volt peak-to-peak signal, which you'll see is just a separate winding off the power transformer off the mains. So this is mains voltage reduced to nominal 1 volt peak-to-peak. Originally, the idea was you could use this as a reference voltage. Because the other thing I should mention about this scope is there's no calibration. There are no real units. First of all, this is not a triggered scope. It's a free-running scope with sync, and that means you won't see milliseconds per division or anything like that. Instead, you're going to see free-running frequencies. So right now, it's running at its lowest frequency, which is it's about 1/3 of 60 sweeps per second, and I can adjust that. But I'm not going to start demoing the scope now. We'll have a much nicer demo later on. So right now it's synced to display 3 cycles of 60 hertz. If I wanted to run it at exactly 60 hertz, I could do that, and there we go. Now I know that it is sweeping at 60 hertz. Great. And you can change the you keep it in sync. You can change the running frequency all the way up to 500 kilohertz. The scope itself is rated at 5 megahertz input. That's its frequency response, which is kind of laughable by modern standards. But back then it was acceptable, it was respectable. You could do actual work with 5 megahertz, absolutely. So right now it's looking, and similarly, just like on the, this isn't triggered in any way. On the vertical side, there's no volts per division setting. There's just an attenuator, and right now it's AC coupled, and it's, you know, it's times 10 attenuation. If I change the attenuation, I can make it bigger, smaller, and I can adjust its size with the vernier control. But it's not calibrated. So, getting long story short, the idea was Heathkit provided you with so-called 1 volt peak-to-peak output, so you could then use that as a reference and say, okay, so this must be, well, 1, 2, 3, 4, more or less. So this, here we go. Here, I just calibrated my scope, right, so that each vertical division is now a quarter, you know, 0.25 volts in theory. And I guess if you had nothing else to go by, if that's all you had in life, never mind an AC voltmeter, well, that'll have to do. But of course, the so-called 1 volt peak-to-peak output is just a separate, isolated winding off the power transformers. So it's entirely proportional. Whatever you're getting out of here is entirely proportional to your line voltage. And line voltages do shift over time, and they've certainly shifted over the decades. So, be that as it may, that's what it's being displayed. You also might notice something interesting, and that is that this is if this is line voltage, it's a pretty crappy sine wave. It's sort of clipped at the top here. Let's make it more obvious. And it's not, in fact, it's not symmetrical. For a long time, I wondered, why is that? Is that my scope? And then eventually, someday, I got a real professional oscilloscope and toss it on a transformer on line voltage, and I realized, oh crap, that's what my utility is feeding me as a sine wave. So yeah, something gets lost in translation between, I guess, the beautiful sine wave that comes out of the hydroelectric plant and your outlet. And this is what comes out of your outlet. In fact, my portable inverter generator that I used to use to back up the house provides a much nicer sine wave than this. In fact, a perfect sine wave. So much for my utility company. But I digress. This is anyway the Heathkit 102, and we're going to go inside and have a look. And just for the record, it is my utility company. It's not the scope. Here's a 10 kilohertz, very low distortion sine wave on the scope, which looks pretty perfect. So the scope will just display whatever you give it. So let's take a tour inside my 50-year-old Heathkit IO-102 scope. And yes, it is unplugged. If we move over to the side here, I'm going to show you what I did to this about 10 years ago when I took it out of the basement, and it didn't work. I mean, the power light, this is a little neon light here, came on, but that's about it. So at least I knew there was power. What I did to troubleshoot it, since it makes sense to start at the power supply, I disconnected all the outputs of the power supply board, and there's several. There's 9 volts, minus 9 volts, 1200 volts here, and so forth. So all of this got disconnected, except the inputs to the power supply, basically coming straight out of the secondaries of the power transformer. And then I started taking measurements, and it turned out all the power supply, all the sections of the power supply were generating more or less their correct voltages, with the exception of there was no high voltage coming out of here. So here are 2 diodes and 3 capacitors, and we'll look on the schematic in a second. This is effectively a voltage doubler, which creates something north of 1,000 volts to run the CRT's anodes and cathode, so it can generate a trace. Obviously, no high voltage, then no trace, no nothing. So I just quickly tested these diodes. The diodes worked. I pulled the caps, and as you'll see elsewhere, tested them, and one of the caps had failed short. I don't remember which one it is, but the other 2 still worked. Clearly I replaced them with new ones. Here's a snippet from the Heathkit IO-102 oscilloscope schematic. This is the top part of the power supply, including the AC input here, which nothing interesting here other than, of course, you can wire it for 110 or 220, and you'll see elsewhere in this video where I've sort of organized this better into a nicer sort of terminal arrangement. The part that had failed and was causing the scope not to work at all turned out to be one of these 3.1 microfarad 1600 volt capacitors, C301, 302, C303. Do I remember which one it is? No, but the good news is the bad news is that one of those capacitors did fail short because we tested it elsewhere in the video, and which means that my guess it was likely part of this voltage doubler section here, not the filter here. And the reason I say that is because these diodes survived the short, and fortunately so did this transformer secondary here, the green and green-red. So my guess is perhaps one of these two, perhaps not this one, but in any case it doesn't matter. There was no high voltage coming out of D, E, or F here when I measured it, and that's where I knew why I wasn't getting any trace at all of any kind or any output at all on the scope. No high voltage. So just to give you an idea of where this high voltage is, and by the way, one of the interesting things is Heathkit, they label high voltage, they label voltages elsewhere at various test points on the oscilloscope for debugging or for alignment. One thing that's interesting is they don't label any voltages around here because I suspect they don't want you probing for voltages north of a kilovolt with your cheap little DMM or however else you would test it. Nevertheless, if you have a high voltage probe, or if you know what you're doing, it's very easy to see if there's any voltage coming out of here in a safe manner. A couple of things that are interesting. So the main negative voltage, of course, the main cathode negative voltage here's the cathode of the CRT, and here's its main negative voltage. It goes through intensity, of course, because that way you can not have any intensity. It also goes that also comes up from F and D and goes through the focus. The output of the focus adjustment goes to a dedicated focus grid, which you can't see here. There are a couple more grids above this one, and then this voltage here goes through a 1 meg resistor and goes to what I'll call the main grid here, pin 2 on the CRT. By the way, where this grid also winds up is on the sweep board. You'll notice a little tail coming off the left here. That also winds up on the sweep board, and it's used for blanking, and more on that elsewhere. The other thing that's worth noting is the filament. There's an extra winding here on the transformer. This is the filament winding, brown and brown. This is something like 6 volts. So you think, it's perfectly safe. I can even play with the filament if I want to. I found out the hard way, don't ask how that was, that that's not the case because of this connection here. So we're taking our 1600 volts, or well, north of a kilovolt, shall we say, and on its way up to, through 1 meg up to the main grid, where we're tying it to the filament. So the whole filament and its winding are right there. Yeah, sure, there's 6.3 volts or whatever, but they're riding on north of a kilovolt. And I found this out the hard way, and I asked, why are they doing this? And I think I know why. The reason you want your filament here to be riding, obviously the potential difference between the two filament connections is only 6 volts, but the whole thing is riding north of a kilovolt above ground. The reason is, I think, you want your filament, you want the potential difference between your filament and the cathode here to be not too great. In fact, to be essentially nothing. And that's pretty much what it is by tying this together. And the reason I think you want that to be the case is if it weren't, if there was like a kilovolt difference between here and here, keep in mind how this thing is built. The filament is in the cathode is a little tube, and the filament is inside that and very close to it. So close that if you had a kilovolt potential difference here, you could arc across it and make a mess of your electron gun. So I believe that's why the filament is brought up to the same potential level as the cathode. So that's basically the super high voltage section of the 102 oscilloscope. In fact, I actually replaced every cap on the board, which is basically just this one, and the 3 high voltage ones. This one here is a axial lead, so that's why it's one of its leads is wrapped back around and shrunk, insulated, and goes back in its hole. But it's a tall axial designed for PC mounting or laying flat, but obviously with the 2 connections side by side. I also, while I was at it, totally re-resistored, if that's a term, the board, since it was easy enough to do so, and a lot of the carbon composition resistors had drifted. Let's see, I did not change the power transistor. It worked fine, although I added a little copper heatsink to it just for good measure. And while I was at it, I replaced some Zener diodes and some silicon rectifiers. So effectively everything on the power supply board is new. So these are the electrolytics and some of the larger resistors that I swapped out of my IO-102 scope. The electrolytics, these are all pretty much vintage. These are the originals that I built into the scope in 1974. The one that actually caused the scope not to work was one of these. These are these 0.1 microfarad to 1600 volts, part of the voltage doubler circuit, which provides high voltage to the CRT's anode and grid. So these do provide on the order of over 1,000 volts. 2 of these tested fine. In fact, if we pick one of them here and I just toss the meter on it, I mean, they tested fine as far as capacitance goes. So here we go. This one is a 0.1 microfarad or 110 nanofarad, so that's fine. That's actually within spec, because these things are what, 20%? Yeah, 20% tolerance. However, this one here was the bad one. It tests at nothing at all, and if I move it to continuity, well, or even to ohms, it's showing 0.1 ohm. So it has failed short. So it has failed shorted. Lovely. So this is what was causing the scope not to develop any high voltage at all. Of course, while I had the power supply PC board out, I decided, well, it's probably time to recap and re-resistor everything. Here's an example of one of the other electrolytics. These are cute because the innards of the capacitor can rotate independently of the cardboard tube. Anyway, this one's a 30. This was 30 at 200, and so if we hook it up, correct polarity, and we put it back on capacitance, we get 57. It actually climbs up. Last time I looked, it went up to about 60 and stabilized there. So double the capacitance. It could easily be just it's leaking, or it's electrically leaky as well. So anyway, that's pretty typical of what's been happening, or what happened to these capacitors over the 40 years that they've been in the scope, just sitting there. And as you might expect, these are the 2-watt resistors, I think, out of the power supply board as well. These had pretty much, at least all the ones I checked, had all drifted upwards in value, typically between 15 and 20% higher than their ratings. And as you can see, they all have silver bands, so they're all 10%. So needless to say, I totally re-resistored the power supply board as well as recapping it. While I was since I was recapping the power supply board and I had the whole thing open, I took the opportunity to recap the entire scope. So what you're seeing here is the horizontal amplifier board that runs the horizontal deflection plates and amplifies the horizontal section. All of its caps, electrolytics, I should say, are new. Same thing with the sweep circuit board. Its electrolytics have been changed. One mod that I remember doing 40 years ago, 50 years ago, when I got the scope, was this little slide switch. This little slide switch basically shorts across the input cap for the external in horizontal. The scope can take an external horizontal. Instead of using its built-in sweep generator, you can actually feed a signal into the x-axis. But the way the built kit was designed, that is always AC coupled. Unlike the vertical section, you can't choose between AC or DC coupling, so it's AC coupled. I wanted it to have an option to be DC coupled, and all that entailed was basically adding a slide switch which would short across the beefy input capacitor here, which basically couples whatever you send and protects the rest of the circuitry. Why did I want a DC coupled horizontal input? So I could use this as an XY display coming off two D to A's off of a microcomputer, generate some interesting patterns. So that's really the only significant mod I made to the circuitry. Here's the other side of the Heathkit IO-102. Of course, on top, the cathode ray tube, the CRT, which is which has its shielded metal here. The only other board on this side is the vertical input section and the vertical amplifier. The compensating trimmer capacitors here, which are used, so you typically adjust these so you get, if you put in a nice clean square wave, you can adjust it so the corners of the square wave don't ring and are nice and flat. Apart from that, it's very, very similar to the horizontal amplifier circuit board. And of course, it got recapped as well. Finally, not that long ago, I actually found the AC wiring connections kind of ratty, so I decided to totally overhaul them. As you may know, like most Heathkit equipment, the transformer, by the way, the transformer is housed in this aluminum box, so it's totally shielded, or the rest of the scope is shielded from it, which is a good thing. But the transformer has a split primary, so you can wire it either in parallel or in series for either 120 or 240 volts. And there was the normal 5-lug terminal strip. And this is the original 5-lug terminal strip and the original chassis mount fuse holder, as well as the corroded screws, which I replaced. I just didn't like the way this terminal strip looked after 50 years. It got corroded, and besides, all the AC was exposed, so I thought I could do better. I replaced all that with a beefier terminal strip, where the AC comes in, the hot side of the AC comes in from the line cord and goes straight to this fuse holder. I'm not terribly proud of this fuse holder, but it replaced the chassis mount fuse holder, which was a little more of a shock hazard. At least this thing's insulated. But whether this is actually AC rated is open for discussion. Ideally, I should simply replace this with a panel mounted fuse holders sticking out the back, like most test equipment might have. But I haven't gotten around to it. I probably never will. Apart from that, from the fuse, it goes back out. It goes to the power switch connections, which are here, then comes back. It goes to a PTC, which limits inrush current, which is something I simply added for the heck of it since I had one. So this limits the inrush current into the scope, and in particular into the transformer and the CRT filament. Hopefully maybe prolong their life a little bit. Then it goes back out and then goes into the primary windings, which if you select the right jumpers here, you could actually just unscrew these things, pop in a new set of jumpers, and it would be instantly rewired for 240. I thought that was a neat thing to do, even though I never, ever plan on running it on 240 volts. But it makes a better voltage selection mechanism than resoldering primary wires onto a terminal lug strip. And besides, the thing has an insulating cover here, the whole strip. So that's how I redid the AC input section of this, and it's working quite well. Although eventually I'll drill a hole. I don't like drilling holes in Heathkit equipment, but eventually I'll drill a hole and put a panel mount fuse holder and simply wire it to those two terminals. So that's this side of the scope. And while I was ordering new electrolytic and capacitors and, high wattage resistors, I kind of went to town with Mauser and NTE Parts Direct, and I wound up ordering a complete new complement of new caps, high wattage resistors, even low wattage resistors if I didn't have, and also a complete complement of new semiconductors, which I chose to get as from NTE. Elsewhere, I'll post the parts substitution list for all the semiconductors in the IO-102 and the equivalents that I found. So if I ever have to rebuild any portion of the scope, whether it's semiconductors or capacitors, I'll have plenty of parts. My obsession with spare parts for my IO-102 scope probably extends a little bit too far, because as you may know, with any kind of Heathkit vintage test equipment, audio equipment, any equipment, or any vintage equipment that's transformer operated, the hardest thing to find if it fails in terms of replacement is the power transformer, because these were typically custom made, particularly for Heathkit, with a specific set of windings to enable the kit. And so usually if a power transformer blows one of its windings, that's basically the end of that whole piece of test equipment. Fortunately, on eBay, I found a seller who was selling the exact power transformer for an IO-102 scope in its original box, and obviously new old stock or unused, a little rusty on top, but I did check the windings and they are all perfectly fine, and you can see all the leads are more or less their original color because they haven't been exposed to sunlight or anything, and well, they all check out perfectly fine. So I didn't power this thing, but I did ohm out all of its windings, and it is fine. So if ever something happens to the power transformer in my IO-102, well, it'll be a bear to replace, but at least it will be easily fixable. But the obsession with spare parts for the Heathkit IO-102 scope doesn't stop there, unfortunately. This wasn't intentional, but I happened to be perusing some surplus parts sites and came across this, a 5DEP1F, this case Hitachi CRT, as new old stock, and this one really does have 0 hours on it, and a beautiful getter, and is in pristine condition. And of course I did test it. How? By simply plugging it into my IO-102, and of course it works just fine. So it's kind of nice. It wasn't that expensive either, so it's always nice having a spare set of spare CRT for your display. And at this point, it would seem that I have almost everything I'd need. I mean, I'd have to add some potentiometers and maybe a few chassis parts, and I could actually build myself a second IO-102 scope if I really wanted to. But of course, that's not the point. The idea is just to be able to replace absolutely anything that should break, in the unlikely event anything really should break on the IO-102 at this point. Well, one last demo of the IO-102 scope. Here it looks like it's showing a sine wave and a square wave. So you would be mistaken, but you could think that it's a dual trace scope. Of course, it isn't. What's really going on here is I have it connected to the Heathkit's ID-101 electronic switch. This should more properly be called, perhaps, an electronic two-channel trace multiplexer, because that's what it is. It's basically chopping the two signals at its input here and alternatively displaying pieces of them on the output such that they both show up. I'm not going to spend a lot of time on this because it's probably worthy of its own little video as well. And of course, since I needed ultimately a source of sine and square waves, what better than Heathkit's iconic IG-18 sine square audio generator, which can generate really nice, very, very low distortion sine waves and square waves from 1 Hertz to 100,000 Hertz. And so I'm using both outputs concurrently into the switch, and these are being combined into what looks like dual trace, but is really one trace being chopped up quite a bit. So that's it. There's the setup. By the way, you'll notice that I'm quite partial in my choice of Heathkit equipment to this 1970s styling with these particular Heathkit knobs. So pretty much all of my Heathkit equipment uses these knobs. The IO-102, of course, was mine from 1974. The IG-18 I got a little bit later, but not much, and built it. The ID-101 switch, electronic switch, that was an eBay find a few years ago. Surprisingly, it did not need any restoration at all. It worked just fine. It just needed alignment and calibration from the manual, and that was it. The IG-18 has served me extremely well for, I guess, on 50 odd years now. The only modification I made to it was to add Data Pro, now 21st Century Heathkit's total harmonic distortion improvement kit and meter damping. So the sine waves that come out of here have always been extremely pure, and now they remain even more so. So this the sine square audio generator certainly continues to serve me as such in actual, with actual work testing. Whereas the electronic switch, not really, because if I ever need a dual trace scope, I pull out my modern digital dual trace scope, and so the it and the IO2 really retain their curiosity and historical factor value to me, and that's why I keep them in good working order. And again, the IO-102 was rated to 5 megahertz bandwidth, so it's worth switching everything. But everything you've seen so far is on the order of 1 or 5 kilohertz sine waves in various forms. So it's probably worth switching to a modern signal generator and seeing what we can get out of the scope. Right now we're at 100 kilohertz. This is where it would be in the on the sweep selector. So this is 100 kilohertz, and we'll just keep going. We'll just keep going up. 200, 300, 400, 500, 6, 7, 8, 9, 1 megahertz. So let's readjust our sweep frequency here. So there's 1 megahertz, 2 megahertz, 3 megahertz. Oops, let's try and sync up again. Again, this is not a triggered sweep scope, so it is syncing on the input, and then to sync up its sweep generator, which is free running. Actually, wait, that's 1.2. Let's go back here. 2 megahertz, 3 megahertz. Notice we're dropping off in amplitude. There was 1 megahertz, 2 megahertz, 3 megahertz, 4 megahertz. And this is what 5 megahertz looks like. So you notice that the amplitude dropped off a certain amount within its spec. And this is how it's rated. So I can dial it up. Actually, we can go to the final sweep frequency and try and get a waveform out of that. There we go. So there's 1, 2, 3, 4 cycles of 5 megahertz. Is that going to be it? Yeah, that's at the top end. So this is the top end of its sweep range, and obviously the amplitude is down, but still within spec. But the linearity went left but to be desired. So will it display 5 megahertz? Absolutely. We could even try and go a little bit further. 6, 7, 8, 9, 10. There's 10 megahertz. Let's see if we can coax it into displaying some number of cycles of this. Oh, there we go. It came and went. So there's 10 megahertz. So now the amplitude is way down below its spec, but it's still displaying something. And I could bump up. I suppose I could bump up the vertical sensitivity, turn down the attenuator, turn up the amplitude. This is at its max, and here we go. Oh, by the way, this is a 1 volt peak-to-peak sine wave coming out of the Unity signal generator. So yeah, there's 10 megahertz. So will it go past its 5 megahertz rating? Yes, but not within its response spec. But you can still get stuff out of it, and that's pretty much where it ends for this scope, because it's all the way at the max of its sweep frequency.